All right, here we are. Welcome everyone to our next session on travel behavior research. Today, last session before the Christmas break. If you're celebrating Christmas, you might wonder, why the heck do you need to have a class just the day before Christmas Eve? Well, that's what the university set our schedule for, so we have another class today. But then we're going to have Christmas break or winter break. There will be a break for 2 weeks, and actually need to add another week of a break because I will be at a conference. So this is the last session before the break that we have here together. Now, what I want to talk to you about today is discrete choice analysis. We had the theory that we talked through last week. We're going to do a quick refresher on what we talked about last week. And then we're going to go into R and we're going to apply this and see how do we calculate a discrete choice analysis in R, and what does R give us? How can we read the results? What do we learn for travel behavior analysis if we do estimations in R? With that, let's first do a quick refresher. What we talked about last week was the difference between regression analysis and discrete choice analysis. And I simply summarized what we talked about last week here in one simple slide again. So in regression analysis, the dependent variable is a metric variable. So it's something that's a number. It's usually assumed it goes from minus infinity to plus infinity. Whereas in discrete choice analysis, the dependent variable is always a nominal variable. It could be an ordinal variable, but it's something that I can name. So in there, I calculate the probability that a certain outcome is selected. So in transportation, the most common is mode choice. We do mode choice in a discrete choice analysis because it's a distinctive choice between auto, bus, train, walk, bike, and what have you. But discrete choice analysis is also used in marketing research extensively. For example, which kind of butter you buy, which brand of car you buy or rent. These kind of decisions are represented in discrete choice analysis. Regression analysis is almost always unsuited to predict a percent share value. So if you try to predict what is the share of people who use the bus, regression analysis performs extremely poorly and is usually unsuited. That's where you use discrete choice analysis because it's really built to calculate the percent share. But regression analysis is very suited to predict a number, such as the price. Yeah? So what is commonly done to understand the impact on housing prices is the so-called hedonic regression analysis, where people feed in a lot of attributes of different dwellings, such as dwelling size, dwelling quality, maybe on which floor the apartment is, whether there's an elevator or not, and also the location, often expressed by how close it is to the city center. And this can be used to estimate the price of a dwelling. A number cannot be predicted by discrete choice analysis because it's really meant to create a probability for a discrete option for a nominal variable. Well, and the independent variables in either case can be metric or nominal. So you can have variables such as distance to the city center, which is a metric variable, but you can also have nominal variables such as elevator available or not. And I have an example here. So kilometers driven as a function of household size, car ownership, income. That would be an example where regression analysis should work quite well. But then another example for discrete choice analysis is if you select a mode, a travel mode, as a function of travel time, travel cost, number of transfers, weather, and what other attributes you try to consider. So that is the distinction, and that's something that's important to understand in which case you apply which one. So what really is necessary that you understand is that for regression analysis, the dependent variable is always a metric variable, whereas for discrete choice analysis, the dependent variable is always a nominal variable. Are there any questions about the distinction between regression analysis and discrete choice analysis? Good, and as I said earlier, the two are related, so a lot that we explored for regression analysis, we will see again in discrete choice analysis. It's just a dependent variable is different. But it also helps that we spend quite some time going through regression analysis because of many things, how we calculate them and how we interpret the results, very similar between the two methods. So that's why it helps that we have the regression analysis in our skill set now when we talk about discrete choice analysis. So Akshay Gupta asked the question in the chat, nominal and metric variable. Can you explain what you mean by that? Because I'm not sure I understand what you're trying to say here. Oh, you want to know what's the differences between nominal and a metric variable? Can someone say what's the differences between a nominal and a metric variable? Someone remember?
I believe a metric variable is something where the number actually matters, in a sense, right? There's an order to it, whereas a nominal variable is sort of just, you can't say whether public transit is greater than a car, but you can say that they're different.
Yeah, that's right, that's right. Okay, so you have one example now for discrete choice, which is different modes. Can you give an example for a metric variable?
Time or price, or just something that has a, that we can count.
Yeah, exactly. Yeah, it's a real number. Yeah, a real number is a metric variable. A nominal variable is one that can have different states, such as male or female, or I buy this car, yes, or I don't buy this car, or which transit path I decide to buy. Yeah, that is a nominal variable. All right, good. So last time we also said already that regression analysis, in regression analysis, we call the dependent variable y or f from x. In discrete choice analysis, we call the dependent variable utilities. It's a utility of a certain option, which we then can use to calculate the probability to select that option. And we said the utility is expressed as the model component or observed component V, and the residual or unobserved component epsilon, which is the error term, right? So when we look into mode choice, we can describe probably quite well the travel costs by different modes, the travel price by different modes, whether there are transfers required on transit. We maybe can also add some variable on comfort of different modes, but there will always be a certain part of the decision-making that we cannot express in data. That could be the prejudice someone has against a certain mode, or the habit that someone has, or the lack of information, how fast it actually would be by transit for a person who usually drives by car. So these are things that we cannot measure well. And those are buried in the epsilon, which is our error component. So, and this describes utility U for a decision maker and for the alternative I. The alternative could be different modes. So epsilon can never be calculated because it is unobserved. Yeah, it's different for every user, but every user deviates a little bit from the calculated utility because there are unobserved portions. So when we do model estimation, we drop the epsilon because we can't express this, and then we use the lowercase u to calculate utility. So we express this, the utility of bus is some constant plus beta 1 times travel time plus beta 2 times travel cost plus beta 3 times transfers. And I guess I should make plus dot dot dot, because you can add a lot of more components here if you have the data and if they're relevant for this particular choice. Okay, but that's the notation we use from now on. So we use the lowercase u that expresses the utility of a certain option of an alternative. And we know there's also this error term, but we cannot estimate this, so that's why we don't write this any further. Now, I just went over this quickly. We have this beta 0 because we know this already from regression analysis. This is our constant. Yeah, we always have the constant, and the same is true here in discrete choice analysis. So it's the so-called alternative specific constant. Yeah, so we call this a little bit differently. In regression analysis, it was simply the constant. Here we call it the alternative specific constant because it's a different constant for every option. So if you have 5 different options, they all have different constants, and they express everything that is unobserved about this particular option. So the alternative specific constant accounts for aspects that are not covered by the data when we estimate parameters. And that's often something like comfort or safety, or could also be an attitude someone has towards a mode or a habit or a prejudice. We call those the unincluded attributes. So things we know that affect mode choice, but we're not able to measure them, and therefore they are unincluded. And we specify the constant by setting one of them to 0. And it doesn't really matter which one we set to 0, but one of them we set to 0 just out of convenience, because that allows us to compare the constant for other modes against our base alternative. And mathematically, it makes 0 difference which one of these you set as your base alternative. Usually we take the alternative that is chosen most frequently. And then we can say beta 0 for bus has the value of minus 0.2. And then I can compare this to the auto. So in comparison to the auto mode, the unincluded attributes make bus 0.2 less attractive. And that's why we like to set one of them to 0, because then we can talk about them more easily than if we had one on all of them. But mathematically, again, it doesn't make any difference if you do this. It's just automatically, it's a convention that we always set the most common alternative constant. The constant of the most common alternative to 0, and then we can compare other constants against our base alternative. So that is the idea of the constant, which we know already from regression analysis, with the only difference here that we have a constant on every alternative, but one of the constants is set to 0. Now, in this example, the parameter on travel time is the same parameter on all alternatives. It is possible, however, to distinguish this. So in this first case, we call this generic parameters because it's the same beta 1 for auto and for bus. Yeah, this parameter is exactly the same value for all modes. And this is the default solution. So whenever you do model estimation, this is what you do first. This is a common thing to do, to have a generic coefficient that is the same across all alternatives. The only one that differs across alternatives is a constant. The constant is always different for each alternative, but the other coefficients commonly by default are generic, they're the same. It is possible, however, and it is very well accepted, to also estimate a different coefficient on other variables. For example, on travel time, there could be beta 1 for auto that is different from beta 1 for bus. Or cost, beta 2 for auto, beta 2 for bus. Those can be different coefficients. And the idea is, well, if you use generic coefficients in the first case here, the argument is a minute is a minute. So it doesn't matter if I spend this minute on a bus or in a car, it's always a minute. So the beta value should be the same because it's just representing a minute of my time, which is a disutility. That's why this beta parameter, this beta 1 parameter, always needs to be negative. The more travel time I spend on a mode, the less attractive it becomes. And so the argument could be a minute is a minute, so this should be the same. But sometimes people argue for alternative specific parameters, where the argument is it should be mode specific, as time may be perceived differently on different modes, such as a minute on a bus might feel longer than a minute in the car. Yeah, and this goes back to those unincluded attributes that we cannot describe really well, such as the comfort level of the car, to have the car for yourself and to be able to sing along to the radio, which you usually would not do in a bus. So this is a difference. So that's where you could say, well, the travel time in the car, I value less onerous because I can sing along to the radio, whereas the travel time in the bus feels longer because I cannot chant along to the Christmas carols. So this is where people argue, well, we can use a different parameter on travel time for different alternatives. And both is done very frequently, and both are right solutions, both are acceptable solutions. I would argue in many cases, we try actually to get different beta parameters for each alternative, because we know that people perceive things differently across different modes. But then we look at the parameters that we get, and depending on how good our survey data actually is, the estimated parameters make sense or not so much. And so if they don't make much sense, then we rather go to a generic coefficient, which is often a fallback solution if our data set is limited and we don't get a parameter through estimation that is reasonable. Let me give you another example of why we would distinguish travel costs by different modes. I mean, you could say, well, if I pay €2 travel costs on a bus or €2 to drive in a car, that doesn't make a difference. But then if you have a car sitting in front of your door, then the money you'd spend on driving the car, you don't feel as much because the purchase has already been made. The insurance for this year has already been paid. So at most what you pay is gas, but even for this particular car ride, you don't pay the gas for this ride, but you filled up your car last week. And so it doesn't feel like you're investing €2 to make this car ride, even though you might be investing €2. Whereas on the bus, if I don't have a transit pass, well, I have to buy a ticket. So in this moment, I have to pay €2, and that feels very different. And so you could call this another unincluded attributes, which is the difference between out-of-pocket costs and costs that are hidden. But often we cannot represent this very well. So that could be another argument why you distinguish betters, and here why you distinguish a cost parameter between auto and bus, where I would expect that the bus parameter is more negative because it's more an out-of-pocket cost, whereas the auto parameter, cost parameter, people might not notice as much how much they pay on maintaining a car. Yeah, so that becomes really difficult. So once in a while, your car needs to go to the garage, get a repair, but you don't mentally, you don't put these costs on every individual trip, but it's more a one-time expense that you have to pay to maintain this level of mobility, to maintain access to a car. So those, I think, are reasonably good arguments why we estimate separate coefficients for different modes. Now, how do we do this in R? In R, there's a package, and it's called the M-logit package. This is the most common package that is used for discrete choice estimation. And there are other packages, and very famous right now, very popular right now, is the Apollo package, but it's a little bit more involved to use, so I didn't want to go into this here. So we work with the M-logit package because there's a lot of documentation on it out there on the web, and it's relatively easy to use. So to use this, we need to define which alternatives the user can choose from. And so in our example, this will be modes, because that's the most common example for discrete choice analysis and transport analyses. You identify the independent variables, something like travel costs or travel times. And then the way you write this in R is you tell R what is the dependent variable, what is the choice. In this case, this would be mode. And then just as we had this in regression analysis, we use this tilde to then list all the independent variables that you want to consider for mode choice. And now here's one thing that gets a little bit more involved, because it's not simply a list of independent variables as it was for regression analysis, but rather there are three different parts, and the three parts are separated by these vertical lines. And these, depending on where you put a dependent variable, the independent variable. Let me start the sentence again. Depending on where you put the independent variable is treated differently. If you put an independent variable in part one, then you get an alternative specific variable. You provide an alternative specific variable such as travel time, and you get one coefficient across all modes. So that is exactly this case here. So for part one, so if you want one variable, if you want one coefficient that is the same across all alternatives, then you put this variable travel time and travel cost into part one. Part three, and I jumped there first, that's the part where you get alternative specific variables with coefficients varying across alternatives. So such as travel time with a different coefficient for each mode. So this one, if you put a variable into part three, you're gonna create different estimations for each alternative. So each alternative will have a different coefficient. That's what part three is for. And then we also have part two here, which was not shown on the previous slide, but part two would be something that refers to the decision maker, such as the income of the traveler, the age of the traveler, whether the traveler has a disability or not, whether the traveler has access to a car or not, whether the traveler owns a bike or not, whether the traveler has a driver's license or not. So these are independent variables that refer to the decision maker, and those go here into part two. And we're going to play with this in a minute, and then I think it will become very obvious. And this is the syntax that you use in part two. Where first of all, you need to install a package, which is called mlogit, if you haven't done this before. But this is only a one-time thing that we're going to do now in a minute. And then you never need to do this again until you get a new computer. And then you load the library mlogit. There's a first step where you need to transform data. This is command mlogit.data. And we're going to go through this when we look at the code, what exactly goes into this. Then there's one step to estimate the coefficients. And remember here we had LM for regression analysis. If we do a logit model, we do mlogit. And that's here is showing essentially what we saw on the previous page. So you tell the dependent variable, in our case, will be mode choice. Then you have the three parts. The first part for alternative specific variables with one coefficient across all options. The third part is for alternative specific variables with a different beta parameter for each option. And the second part is where you put variables that refer to the decision maker, such as age or income. You tell it where it shall get the data from, where the weights are. And then here's our good old friend, summary of this object will provide us with the estimation results. That's the same command as we had in regression analysis. And with that, I would like to jump into some work with R. So let's all go ahead and open R Studio on your computer. And if you go to Moodle, you will find that I uploaded some data there. And I would like you to download the data from Moodle. So let me open this one here. Oh, that's not the right one. So if you go towards today, which is here's a lower part, so it's always you get a Moodle a week, right? But now we have it twice a week, so that's why it's a lower part starting here. There's slides from today, and there's mode choice training data and mode choice test data. And I asked you to download both of these data sets, and as always, save them in some location where it's convenient for you to access them. And in the meantime, I'm going to open R here. Close everything that I had here. So let me have a clear start. And I wait just a moment so that everybody can download the data, open R, and then we can go through this together. Okay, and then we get started. So first of all, I click on this plus button on the upper left because I want to create a script. And there's my script, my empty script. So I can start putting in some information here about what I want to get done. And as always, I want to read in the file first. Well, I first make a line here where I write a little bit what this will be about. So this is now discrete choice estimation mode choice example, so that I know later what the heck I'm doing here. And first I want to read in data. So I click on files and I navigate to the directory where I have the files. It's here, 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 here. So this is where I have my data. And you move to the directory where you have saved your data. And then you click on this more button up here and say set as working directory. That sets the working directory and it also gives me the command here at the bottom. So I'm gonna copy this here, put this here into my main document, because then I can rerun this in the future without searching for the file here in this browser. Okay, this is already set. And then I need to read the data. And call this fit data. I want to read in with the command read CSV. I say what my file is called. It's mode choice training data.csv. And it's also a good habit to define the separator as comma. And I read this. And then what we always like to do first is we like to run the summary to get a sense of what's in this data set. Big data, run this. So I get an overview here at the bottom, what's in the data. And actually I need to increase the font size again, right? Because I moved this back to a convenient size for myself. This is maybe a little easier for you to read. I need to run this again, I guess. So format it here. So it tells me there is a mode, which is a character variable. Then I have age ranging from 14 to 78 with an average of 44.24. Gender appears to be 0 and 1 for gender, male and female. Income range from 128 to 9,204. Household size range from 1 through 8 with an average of just over 3. Auto availability is defined here as values from 0 to 7, whereas bike availability is 0 and 1. So apparently bike is only yes, no. And then we have some variables here that describe time to walk, time to bike, time by auto, and time by transit. So these are the travel times for an alternative. And then the last column has a weight. Okay, but there seems to be nothing out of the ordinary. There are no undefined values. I know this, that there are no undefined values, so we don't need to do any cleanups this time. Don't need to exclude any NAs as we had this in earlier examples. So it makes it a little easier for us. Now, the only thing I can't see very well here is what mode looks like. Does someone remember how we can see which values mode has? Anyone idea for a command to find out the values of mode? Factor. Factor is a transformation of mode. No, actually, factor is a transformation of an integer variable into factors. So a number variable into factors. No, I don't think factor will get us here. No problem. Thanks for trying. I appreciate it very much. Anyone else an idea? It's okay. I know there are lots of commands here, so I'm not expecting you to know this by heart, but I just thought I asked if someone has an idea. Unique. I like that. Let's try this. Unique. And now I do fit data. And now what I want to look into is mode, right? I want to understand what's in mode. Run this. And yeah, that's a good command. Very good. British McCormick. There we get the dimensions, the variables, the dimensions that are behind our mode variable. Also, I want to see, well, how often are they used? I can also use this table command, fit data at mode, $mode. That also gives me a list of all modes that are in my data set, and it gives me also a count to get a sense of, okay, auto is the most common mode. That's interesting. Good. Then the next thing that we did already in regression analysis, so it's just a repeat here, but it's helpful to do. Well, first let me also put in some comments here. Read in data so that we know what we are doing. And now I put another command here, check for correlations. So we had this already, right? We had this library core plot. So if you have not installed this yet on your computer, you will get an error message when you run this. If you need to install it, you go to Tools, Install Packages. You click on Install Packages, and then you can select here Core Plot. I'm not doing this now because it's installed on my computer, and it should be installed on all of your computers already because we used this method before, this package. So I run this library core plot, and then I define, I don't know, I call this core matrix, correlation matrix, and I define this as core of, I need to write data frame. And now I can write fit data $h, fit data $gender. Yeah, so I add now all the data points that I want to see, where I want to check the correlation. Take income, household size. And the auto availability, fit data, bike availability. And then if I run this, then it now created a new object, which is core matrix. And then I can plot this core plot. I need to feed in the core matrix. So I just defined, let's say method equals number. And then I run this. And then it creates here.
I had a quick question.
Yes, go ahead.
For line 13, would it be possible if you could,
Sorry, there's a feedback. It's hard here. Please say it again.
For line 13, could you scroll a little because I didn't get the last fit data.
Sure.
Sure. Fit data bike available. Okay, thank you.
Of course. I let it stand like this for a moment because I'm sure there were other people who couldn't see this when I quickly clicked return. But it produces us this matrix, which is something we have seen from regression analysis already, right? Because we look here at the correlations. And it provides us a color to give us a sense of how correlated values are. There's some numbers that are very faint because they hardly have any correlation. We see a negative correlation between household size and age, meaning the larger the household, the younger the person is likely to be, which is intuitive because you have children in larger households. There's a positive correlation between household size and income, meaning the larger the household, the higher the income tends to be. That's also intuitive, and most other correlations are fairly faint. Now, this line was rather cumbersome to write, right? Because I had to define all the different variables that I want to include. There's also another way that you can do, which is I call this core matrix quick. Yeah, and just add a Q here and do the same thing, core, core. And now what I'm going to do is a little trick. I just want to show you the trick to create essentially the same thing, but it's easier to write. You need the square brackets, comma, 2 to 7. And what 2 to 7 means, that is the variables that I want to include. Now, the first one I cannot include because it's a character. I cannot include a character into a correlation plot. But 2 to 7 means I include 2, 3, 4, 5, 6, 7. So from age through order availability, I include, and these in the end, I didn't include those because this is my dependent variable, so I'm not so worried about correlations with my dependent variable. And the weight is something that I just use for weighting. So I also don't need to include this one. So this is a much shorter way of writing than writing out all these different variables. And that's why I just like to introduce this here. I run this, and then I can do core plot from core matrix quick, comma, method equals number. And I run this, and it produces essentially the same thing. It formats a little nicer here, the names of the variables. So I don't know, actually, Gupta, what you mean. Explain this command again, command QX. This is simply a simpler way of writing what we wrote extensively, where we had to write a long line here that doesn't even fit into one line. Also, I can make it 2 lines, right? That's easier to see. Where I had to write a long command here, I can write in a much shorter way by simply defining which columns I want to include. And I want to include columns 2 through 7, and that produces the same plot, but a little bit nicer to look at. So there is no big problem in terms of correlation, but there are 2 values I need to watch out a little bit for. Household size and age is some correlation. Household size and income is some correlation. So I need to be a little careful about those, but nothing too worrisome. So nothing that we need to exclude directly. Okay, now we need a new method, because now we do yes.
Can you explain the correlation issue again? Is it just the intensity of the color or the numbers in it?
That's right, that's right. Okay, yeah, let me say this a little more clearly. What these numbers give us is the R value. So the R, the correlation coefficient R. That means the closer this coefficient is to 0, the less correlated these 2 variables are with each other. So there is no correlation between gender and age, because you find females and males across all age ranges. So that's why this number is so faint that I cannot even read the number. But there is a negative correlation between household size and age, which suggests the larger the household size, the more likely it is that the person who responded to the survey has a younger age. Or if it takes the other way around, people who have, the older the people get, the more likely it is that the household size is smaller. The children have moved out and retirees, for example. But this table gives us the R values, which can be positive or negative. They can range from -1 to +1, where -1 means they're perfectly correlated in an inverse way. So one gets bigger, the other one gets smaller. +1 means they're correlated perfectly in the same dimension, in the same direction. And 0 means there's no correlation between these 2 variables. And when we talked about regression analysis, we said we have an issue if the correlation between variables is too large, because then the coefficients cannot be interpreted well anymore, and the method doesn't identify the impact of each variable properly. If you have 2 variables that move in the same direction, the method is not able to detect the real impact of each of those. And that's why we check for correlations before we do an estimation. And so we did this in regression analysis. We produced these plots to identify where do we have major correlations. And the same we do here. And so we see, well, there are 2 variable pairs that have some correlation. So we need to watch out, need to be careful with those. But we don't see any dramatic correlation here. Does this give sufficient background, or are there any more questions on why we are doing this and what is shown here?
Yes, it's well understood.
Okay, good.
Thank you.
Yeah, thank you for raising this, because I'm sure many others were wondering this as well. Why are we looking into correlations here? So I was just starting now with the next step, which is actually discrete choice model estimation. So let me type this here, discrete choice model estimation, just to give a little comment here so that I later remember what has been done. What we need now is a new package, and that's the mlogit package, which you probably don't have on your computer. So you can either go here to Tools, Install Packages, and type mlogit. Don't choose the second one, just the mlogit package. Yeah, again, that's under Tools, Install Packages, and then type mlogit. There's also another way. If you want to do this in a command, you can also write this install packages, and then you provide mlogit. If you type this command, it does exactly the same thing as if you click on Tools, Install Packages, and type mlogit. Whoops, if you can type it correctly. There you go. Yeah, so this is the same thing, it does exactly the same thing. I'm not doing this on my end here because I have installed this before. So actually I'm gonna comment this out. I don't need to install this again. I know it takes just a moment to download the package and get it up and running. I assume this is complete now on your computer. And then what we need to do next is we need to load this. So we do this with library mlogit loads the library. Yeah, this is not an arrow, actually I looked at, but this is something that it's doing automatically in the background in order to install the mlogit package. So no worries, this is just for information. It's not an arrow. So if you type this line, library mlogit, and run this, you should get something like this, that it's loading this. But if you get an error here, then the installation didn't work out. But if you get something like this, then it's just loaded correctly. Okay, so if I go back here to the slides, we said that first we need to install the packages, which we did here. And the next step is we need to do some data transformation. And that's exactly the step that we are going to do now. And data transformation is always a little cumbersome to write, and I always have to look it up. Well, how do we do this again? This is not something I learned by heart, but there is some method in this mlogit package, which is called mlogit.data. And this is the transformation method that we are using. And I feed in the data frame that I have downloaded, that I have read in, fit data. I need to tell it in which column my choice variable is. And the choice variable is in the column mode. So actually, I'm going to open this now by clicking here on the right side. If I click on fit data, it opens it here. And you see in the first column, it tells me which mode was actually used. So the person who answered here, which was a 52-year-old man with this income from this household size, etc., this person answered that this person took this trip by bike. And so I need to tell the actual choice that was made is in the column that is called mode, because this is column mode here in the front. I need to do something else that is called shape equals wide. This is how it transforms the data. There's a way of transforming it to long and to wide. We need this transformation wide. And there's one more thing that I need to tell this transformation step that is called varying equals the columns from 8 to 11. Now let's look again at this data file. The columns from 8 to 11 are the columns travel time walk, travel time bike, travel time auto, travel time transit. So even though this person chose walk, we do have the travel time for walking, biking, auto, and transit. So these are the varying attributes. Those are in columns 8 through 11. And that's why here I type varying equals an array from 8 to 11. It tells us which column numbers vary. Just a moment to write this on your end. And then we run this by clicking the run button. Now, if you look carefully, it created now a new object here, which is called logit data. If you click on it, you will see you cannot read it because you get this error message, because it's not a data frame actually that you can look at. So let's close this again. If you really want to see what this is, what we just created, you need this command view. And you need to say as data frame. You need to transform this into a data frame, and then you can choose logit data. And if you run this, it opens the file. So it opens this object logit data. So I let you see this for a moment so you can type this on your end. It's view as .data.frame. And then the object logit data. And after you did this, let's look at this together for just a moment. What it did now, it created 4 lines for every entry that was 1 line before. And it created a new attribute here that is false or true. So this first record chose this mode bike. So this is true, but did not choose auto, transit, or walk. So those are set to false. It's the same person. That's why the person attributes are all the same across these 4 entries. And it has a travel time for each entry. And it has some more information here that is needed by R. So what it did, this transformation step, it took 1 line from the original file and split this into 4 lines where we have 1 line for each alternative mode. But these 4 lines describe the trip that was described in 1 line in the previous data set, in the original data set. So we don't need to worry too much about what's in here because yes.
So can you just explain me once again the true false one? I'm not able to understand. In that second why it is true, rest all are the false.
Yeah, so this is 1 trip from the previous file and from the original file. And this person actually traveled by bike. And that is why the bike line is set to true. And the other modes were not used for this trip. So that's why they're set to false.
Okay, thank you.
And the second entry, traveled by car. Yeah, and so the car line is set to true. The other entries are set to false.
Okay.
But each entry from the previous line was split into 4 lines, which is just something that's needed by the R code. So let's not worry about this too much for now. It's just the transformation that we need to do in order to run the estimation. Okay, and now we have everything ready. Now we actually can run our first discrete choice model estimation. And I'm going to put here a little command because I want to run multiple ones. So I call this now model with 1 travel time coefficient across all modes. And I should spell across correctly. So, and we go back, if I go back here to what we discussed before, So we said I can use one beta coefficient across all modes, or I can use a different beta parameter between modes. And we said the difference is if I put this variable either into position 1 in part 1 or in part 3. And now for now, we're going to put it into part 1 because we want to have one coefficient that is the same across all modes. So let's do this. And I call this MNL underscore fit1. I'm really stuck on the, do you spell across with 1C or 2C? I need to get this right now. I'm just staring at this, I don't know anymore.
1C.
1C, thank you. I just was looking at this. Did I get this right now or not? So, okay, thank you very much, I appreciate it. So now I do the model estimation and I use mlogit. And now first I define what I want to, what's my dependent variable? My dependent variable is the mode. And now comes our friend C tilde. Whoops, where is it? There it is. This tilde, because on the left side I have the dependent variable, on the right side I have the independent. Now we said I want one coefficient across all modes. So that's why travel time goes in the first part. And now I need a vertical line, which looks like this. And I must say, I'm not sure how you get this on a PC. On a Mac, you type option and the number 7, and then you get this vertical line. Oh gee, and that's a German keyboard. So if you don't have a German keyboard, it might even be somewhere else. But on the 7, I have the slash. And so if you push the key with the slash and option, you get this vertical line. If someone knows how you get this on a PC, would appreciate if you all let us know. So if not, so that other people don't have to search for it.
Shift and press the button above enter.
Okay, above enter. Or the shift and the back shift. Okay, thank you very much. I hope this works for everyone now to get it. Oh, and you just put in the chat, that's a good idea, GAHO, because then everybody can copy it from the chat. I should have done this right away. That's the easiest way, very good. Thank you very much. So this is now the first part, which is where I put the independent variable for which I want to estimate one coefficient that is the same across all modes. Then the second part, I put in independent variables that refer to the decision maker. And let's just pick one and say we use age. And we try to explain mode choice by travel time and age. And the third part, which I again separate through another vertical line, has those independent variables for which I want to estimate a different beta coefficient for each alternative. I don't want to deal with this right now, so I set this to 0. I don't want any parameters there. I still need to put a 0 so that R understands which is part 1, part 2, and part 3. Now I say comma, I need to feed in the data, which is data equals, and I take this logit data object that we just created in line 22. And then you know that we always want to work with weights, which we also define here with weight equals weight, because weight is the name in our data set. So here, this variable weight, I need to call to get the weights. Yeah, remember we introduced weights because we want to correct for over and under sampling in the survey, and the weight's correct for that. Good, and then this we can run. And now it just takes less than a second, and then it calculated your first discrete choice analysis. And now comes our good old friend summary. And we say MNL fit1. And I run this. And here comes the summary of our first discrete choice analysis. throw this up here so that you still can see those lines up there. I should do this. Okay, so now what can we see here? Well, first of all, R repeats the command that we put in. So if you want to document this somewhere, it's easy to copy this. It also provides you, for convenience, a table of frequencies of these choices. So this is what it finds in these data sets. In the data set, these are the shares of the different choices. There's an NR method that is used to do this estimation. It had to run for 12 iterations, took roughly a second. This value here is very, very small, very close to 0, which means the result is statistically significant. So the gradient is close to 0, so all is good. We don't need to worry about this too much. What we really want to look at are the coefficients which are provided here. Now, first of all, there are 3 intercepts. Those are our constants. I'll go back to the slides one more time. We had on this slide here, we talked about the alternative specific constants. And we said one of them will always be set to 0 out of convenience, and the other ones will be non-zero values and a different value for each mode. And so here it set 1 to 0, and it chose to set order to 0. Order is the most frequent alternative, so it took order as a base. But as I said before, it doesn't make a difference which one is set to 0. It's just one is set to 0 out of convention. And so we get a constant for the other modes, and these constants represent unincluded attributes. So things that we do not collect in our data set, well, things that we do not include here, we only included travel time and age. There are a lot of things that are not included in the estimate, and those are all hidden now in the intercept. And then we get a coefficient on travel time, which is minus 0.03 and something. That's a very reasonable coefficient. It's very common to get coefficients around this size for travel time. So it tells us the longer the travel time on a mode, the less attractive it is. Yeah, so there's an inverse relationship between travel time and the resulting utility. And then I get also a coefficient on age. And I get this now for each mode except for the base mode, because the base is what it refers to. But it says now, so you can read this the following way. There's a negative coefficient of age on bike, which means the older the person, excuse me. Okay, maybe someone was just not on mute. It means the older the person is, the less likely this person is to use bike in comparison to car. The same on transit. The older the person gets, the less likely the person is going to use transit in comparison to car. And the same is true for walk. And I guess that's intuitive that elderly people are less likely to use these modes of transport. They're more likely to drive. I think this is Australian data, so at least in the Australian context, this makes a lot of sense to me. What it also provides us here are these stars, which tells us something about the level of significance. And remember, we have the same thing for regression analysis. So the level of significance tells us something, how much confidence we have into each of these estimates. And the more stars we get, the better. The fewer stars, or even the dot, means that there's a larger chance that the resulting coefficient is merely random. And we see that we do get significant estimates with at least 1 star on all our independent variables. Not on the intercept, but as a rule, we do not need to worry about the significance of the intercept. We can always keep the intercept. This is something we never need to worry about. So intercept without significance, perfectly fine, nothing to worry about. But independent variables, we only want to include if they are significant, we have a special other rule or a special other circumstance. And then it gives us a few more values here on the model fit. There's a log likelihood. The log likelihood is a unitless number that doesn't tell us anything except when we compare two different model runs. The log likelihood is always negative and should be as close to 0 as possible. The closer to 0, the stronger the model, the better the model explains what is happening in reality. But minus 5,588.7 doesn't tell me anything. It's just if I have two models that are estimated and one has minus 5,588 and the other one has minus 4,000, then I know, oh, minus 4,000 is quite a bit better than minus 5,588. So I would prefer to choose the model with the log likelihood of minus 4,000. Another value we are just more familiar with looking at is the R-square value. This is a pseudo R-square value. It's also called the McFadden R-square value because McFadden invented this R-square value. He was the one who got the Nobel Prize for developing the logit model. It's an estimate that is representing reasonably well. It's close to the R-square value that we are used to from regression analysis. So it's an indicator how well the model is working, where 0 means the model doesn't understand anything, and 1 means the model perfectly represents the observed data. And so with 0.1, not all that great. One could say we represent 10.9% of the variation in the data, but it's not a very good estimate. But at least we explain 10% or almost 11% of the variation in the data. There's a likelihood ratio test, chi-square with a p-value again. P-value is very small, which suggests statistical significance, but that's something we don't need to look into any further.
Hello, Professor.
Yes.
So in this McFadden one, it is every time it is in positive, or sometime in some cases it may go to negative also, negative value also.
Yeah, good point. This
because in every point, every steps, the value is going to the negative direction. So, and the McFadden one is only the one value which is in positive. So it is in this case, or it would be in some other scenario also.
So this value is always positive because it's R square. So if you multiply a negative number with negative number, R square is always positive. And so this is different from the plot that you see here on the right side, where you see that the number can also be negative. But the right side, the plot is showing R, not R square. And the R value can be negative or positive, but R square is always positive.
Okay, thank you, Professor.
Okay, so we said now that auto was chosen as the base mode, and that was automatic because it is the most frequently used mode. We also can change this, yeah, just to see how it show how it works. Change base mode, and I do this by essentially repeating this. I call this model underscore fit2, and I like the space here, it looks nicer. mlogit. And again, I want to predict the mode with travel time and age and no mode varying parameters, and data equals logit data. So I mean, I could have copied the previous row. The weights are also still the same. But now I add one more information here, and that is the ref level, which stands for reference level. And I could set this to transit, my second most frequent mode of travel. So I run this. Oops. I should spell await correctly, otherwise it doesn't work. And then it works. And then I can look at summary. MNL underscore fit 2. And run this. And so now you see, I get an intercept now for auto, bike, and walk, but none for transit. And so now I can compare these parameters against transit. So in terms of unincluded attributes, auto is 0.01 units more attractive than transit. And also here, the age variables, I now get those variables in comparison to transit. And you read it this way: comparison to transit, the older I get, the more likely I'm going to choose car over transit. The older I get, the more likely I'm also to choose bike over transit, and the same is true for walk. Yeah, so I set a different reference level. Mathematically, this leads to the same result, and that's why the R square is also the same. It doesn't change, it's not better or worse. By convention, we choose the most frequently used mode, but I can change this if I need to do this for whatever reason. Okay, let's do another one. Model with varying travel time coefficients for each mode. So here, I'm going to copy now the first one because I don't want to type this all again. So I copy the first model estimation that we did and put this in here. I call this now models fit, MNL fit 3. And now what I'm going to do is I'm going to replace the first part with a 0. And the last part, I put in travel time. Right? And so the difference between part 1 and part 3 is that part 3 is the place where I estimate varying coefficients across mode. And so if I run this and I run the summary, I get this estimation, which looks just a little bit more complicated. But the reason is it is more complicated now because I got varying coefficients for each mode on travel time. And now if I look at this, I get a relatively small coefficient of minus 0.0043994 for auto, and that's small, a coefficient that's relatively close to 0. And the coefficient for bike is much more negative, minus 0.069, which suggests that travelers react more sensitive to travel time increases by bike than to travel time increases by car. And I guess that's very intuitive. Yeah, you would think that if for whatever reason my bike ride takes 5 minutes more, that's more painful than sitting 5 more minutes in a car. And it's even more time sensitive for walking. Yeah, so for walking, people are very time sensitive. We tend to take the shortest path to reduce the walking time. Transit is almost the same as for car. It's even less sensitive to travel time. So for transit travelers are even less sensitive to a slight increase in travel time. I guess it has to do with the fact that many people who use transit are transit captives. So they have to use transit because they don't have a car, don't have access to a car, or no driver's license. And so they don't react as sensitive to zero time on transit because they just have to use transit. But that's just an hypothesis why this is slightly closer to 0 than for car. And you see everything is still significant. Well, travel time by auto is the least significant. It has only one dot, which means the significance is somewhere between 0.05 and 0.1. It suggests that, well, there is a higher probability that this coefficient here came about just randomly. And it's now a matter of the analyst to judge whether this level of significance is still sufficient or not. I commonly include, for travel analyses, I include things that are relevant, significant up to a level, up to a p-value of 0.1, even though I understand there's a certain probability that this coefficient came about just randomly. So specifically, I can look at the p-value. So the p-value is between 0.05 and 0.1. The p-value is exactly this one here. And that tells me there's a 7% chance that this coefficient came about just randomly. Okay, and now I want you to do a little typing by yourself. I want you to do an estimation of I want you to run an estimation where you don't use age, but income and auto availability. Type this here, income and auto availability and travel time differs by mode. So I want you to run an estimation and see what you get out of this. So be quiet here for a moment. I want you to do this by yourself for a moment. So were people able to estimate a model with auto availability and income? And if so, can you say the R square that you got, the McFadden R square? Zero 0.10033. Thank you, Gabriel Hammond. Let me see if I get the same one. So I copy this one here. Then I don't need to do as much typing. And so we didn't want to have H anymore, but rather income and auto, underscore avail. So those are the variables that we need, and I call this now 4. Right, so this is the only change. I leave travel time here because I want to have separate coefficients for each mode, but I want to look at income and auto availability. So I run this. I get a higher R square.
I wrote income, comma, auto availability. That makes sense. Why did you use a plus there?
Well, that's a notation it needs. It didn't give you an error message?
No, which I was wondering.
Yeah, interesting.
Okay.
So it actually
My bad.
stopped after income. So what it did now, it had an intercept and income. Oops, and everything that came after income, it ignored. Yeah, so okay, but that's good to talk about this here. So you put a plus sign, which actually is the same sign that we also used for regression analysis. When we wanted multiple independent variables, then we used plus sign between each independent variable. I wish R would give you an error message if you use a comma there. That's what it should do, but R is not always the strongest on providing error messages. Oh, well. Okay, so I actually got a quite high correlation here with the McFadden R square of 0.31, at least substantially better than what we had before, with the only caveat that I now get some estimates that are substantially insignificant. So there's the income on bike variable that has a probability of 26.5% to be just random. And the variable on travel time on transit has a probability to be random, has a almost 64% probability to be random. That I would not accept. That is way too high. So what I do now, I want to exclude those particularly, because maybe I like the combination of other variables. Maybe I want to run some analyses on order availability and income. So maybe I really want to have those in my model, but I want to remove specifically travel time on transit and income on bike. To do this, I need to define a new variable in my data set. So and I do this way. So logit data $, and I call this now auto. And I define this with this command, if else logit data equals auto 1,0. So I do this, and then we can look at what this looks like. So I run this. Oops, I get an error message. What am I doing wrong?
Do you need to specify that you're looking at the mode for logit data, maybe the $ mode?
Perfect. It's actually, but I'm looking now at this one here, which is actually this one that it's looking for. Very good. Well, this is a very good comment. So it's actually alt it's looking for. So, and this is working now. And now if I want to view this again, then take this command here. So or did it update here? No, it didn't update here. I close this, go here and view this again. Now it has added another variable for auto that is 1 if the mode was actually chosen to be auto and 0 otherwise. So we don't need to look at this here, but this is now how I added another variable. So if the alternative is auto, set it to 1, otherwise set it to 0. And I'm going to do this for the other modes as well. So also for walk, if it's walk, set it to 1, otherwise to 0. And for bike, if it's bike, set it to 1, otherwise to 0. And I do it for transit. If the alternative is transit, set it to 1, otherwise to 0. And I need to run all of these. So now I've expanded my data to have these binary variables 0 and 1. And the reason why I introduced the binary variables is now I can have an interaction. And so the next model is remove. So what did we have here? We had first we had this one here, huh? Income on bike, as it was insignificant. And so the way I do this, so MNL4, I want to overwrite, yeah, because the other one was not significant, I don't need to keep it. So I override this with mlogit. And I want to predict the mode again. Yeah. I put in my tilde. And now I write, I want the interaction of, so it's I, capital I, and it's the interaction of income times transit. And I also want to have the interaction of income and walk. And the rest I leave as it was. So we had here in the part 2, we had auto avail. And in part 3, we had travel time. And then I also need to type the rest again. Data equals logit data and weights equal weight. Start a new line here so you can see the full command. We run this and then we explain this one more time. So there's a summary on MNF_4. I run this. And now what it removed was the variable with income times bike, which was not significant. So I go back up here where we were before. On the income variable, we had the problem that it was not significant for the bike option. And therefore I want to exclude the bike option. I only want to have transit and walk. And I created this variable that's 0 or 1 if it's transit or walk. And then I can multiply the income, I can run the interaction between income and transit, if it's transit, and the interaction if it's walk with income. And as a consequence, I only get the interaction with walk and income and transit and income, and the interaction of bike and income was dropped. Now I still have one here that I need to drop. This is travel time and transit, and I do this very quickly by copying this one more time. So it's not perfect yet. I also want to remove the next one, which is, I also want to add here in this first part, income by transit, income by walk, and I also want to have the interaction on travel time with walk, and I want to have the travel time with bike. Oh, this is the interaction is shown with the star. Travel time bike, and I want the interaction of travel time by car or auto. So make a line break here that we can actually see this. So I'm going to run this. Oh, and now I need to remove travel time here in the back, because I have travel time now in the first part where I have the interaction with walk, bike, and auto. So I don't need the travel time variable here in the back anymore. And I run this, and then I get this result where every variable is significant, and travel time with transit was dropped, and income with bike was dropped. And then I have everything significant, and I'm quite happy with this. I'm also at the end of the session. We're going to pick it up here after the break. I'm just going to open a calendar. So I mentioned earlier that we will not meet when classes officially start again. So I believe classes start again on January 7th. But the following week, I will be at a conference. So that's why on January 9th and January 13th, sorry, on January 10th and January 13th, we will not have a class because I'm in the US and I will not be able to teach this class. So we see here again in this class on January 16th. Very much hope that the new year will also give us back some in-classroom teaching, but we will need to see how Omicron is going to change our lives over the next 2 weeks. If you celebrate Christmas, I wish you a Merry Christmas. If you don't, Happy Holidays to you. And I wish you all a very, very good New Year 2022. Looking forward to seeing you back in mid-January, so January 16th, we see again here in this class. And so long, stay healthy, take care of yourself, and if you can, of someone else as well. Wish you all the best and see you in a few weeks. Take care, everyone. Bye-bye.
Thank you. Bye-bye.
Merry
you.
Christmas.
Happy holidays.
Happy New Year.
Happy
Thank you.